So in terms of the outline of the lecture then, what I wanted to try and do is go through these 4 basic regression problems. So the first problem I wanted to sort of show you how to solve is how to plot variables in both R and E views. So the idea here is that this enables you to cross-check the formal statistical results with graphical analyses. That's deceptively important in practical research work. I've been able to do high-level maths for a long time now. I've not always had the maturity and the experience to really appreciate just how useful this can be. The second problem I want to talk about is R squared. So the idea here is that this measures the proportion of the variability in the data explained by the model. The basic idea is the higher the better. There's some sort of artificial textbook examples that you might see in various books. The point here I would say is that from a practical perspective, anything potentially 0.3 or higher can be useful. And then talk about the t-test. The idea is a t-test, extension of what we've seen before, is to test the significance of individual parameters. And the f-test, again, an extension of what you've seen before. The idea in this case is to test the joint significance of multiple parameters, so sort of hierarchy between the t-test parameters, with an additional multiple regression example. So in terms of variables then, so in this sort of word example I mentioned previously, interested in the relationship between real stock prices and real gold prices, and the real bit just means inflation adjusted. Now I want to try and plot the two variables together. So the idea here is that this would give you a cross-check of the results of a formal statistical analysis. So that's important in real project work. So again, it's something that when I look back at my own career, not always had the maturity and the experience to fully appreciate the value of this. And then the point is that you do the statistical analysis, so you're not just restricted to just looking at the graph and guessing. Okay, so in this example, there is a sort of financial backstory. So there's some suggestion that as the stock price falls, could be a flight to quality, people buy gold, very prescient with the ongoing crisis caused by COVID at the moment. So this increased demand may lead to an increase in gold prices, so a negative correlation from that respect. The reverse may also be true, so people leave gold to play the stock market when the stock price increases because they think they can make a quick speculative profit on the stock market. So in both cases, there would be a suggestion from this that inflation adjusted stock prices and inflation adjusted gold prices should be negatively correlated. Okay, so in this instance, again, there's a sort of backstory which you might want to sort of cross-check by looking at a graph. So in terms of the tactics of this course, so I wanted to try and teach R and E views, but prioritise R. Now it's possibly too much to try and do that in normal times. It's probably going to be even more difficult in the current set of circumstances because we've got limited access to campus and the campus computers. Now in order to compare these, so I'm currently learning to drive now, and I think the comparison between R and E views is like manual and automatic driving. So you've got more freedom in R, but it does mean it's harder to learn initially. Okay, bit similar to, it might be easy to learn automatic, but you don't just want to be constrained by an automatic license. So R is more important. I wanted to show you how to do this in E-views initially. It's slightly easier, I think, if you have to see this in reverse order of importance. So E-views is a little bit easier. R is more involved, but aside to that is it's ultimately better. All the graphical parameters yourself, a bit like having to change gear yourself. So this ultimately gives professional users more control over the graphs and outputs, but it just means it's a sort of slightly harder learning curve to begin with. Okay, and similarly, I think E-views, it's slightly easy to pick it up, but it's ultimately limited, and there's further complications with things like the license and off-campus access. So in E-views then, so graphs in E-views are essentially a passive menu-driven process, a bit like a sort of harder version of Microsoft Excel, which, as we said before, is John Kryptonite. So if you have this sort of E-views work file available on campus, work file, what you would do is variables, price, and price. has to be sort of spreadsheet mode in order to sort of work, and then do quick variables, real stock price, gold price. Now when you do this, you have to sort of do it in order, so that the X variable has to be first, has to be on the left of the thing on the Y-axis, and then click OK. So it's all menu driven. Now that's nice and easy when you're first learning this, but if you've got more complicated examples, then this is a constraint, because you're then constrained in terms of the plotting options that are provided for in the menu. Now in contrast, in R, because you're specifying exactly what the computer has to do, you're actually given more freedom, even if it takes you a little bit longer perhaps to learn how to sort of do these things from scratch, and you've got to think more carefully about what exactly it is you want the computer to do. Again, this comparison between manual and automatic driving. So in terms of plotting variables now then, so the data is on this .text file available on Canvas. So what you'd have to do is save to your USB stick and then read in the data using this read.table command. Reasons for this: essentially, if you make this file path as short as possible by saving onto your USB stick, then you make this as quickly as possible to work. And what I also ought to say here is that on my computer, when I was doing this, my USB stick was the E drive. On your computer, it's possible that your USB stick will not be a drive, in which you have to change the letter here. Now, if you look on this .text file on Canvas, what you should see is there's two columns containing the real gold price on the left and then the real stock price on the right. Now, how you would do this in R is call real gold price the first column and the real stock price the second column. So what we've got here at the bottom of the slide, what you're saying is that you want the real gold price to be identified with the first column of this data set and the real stock price to be identified with the second column of the data set. And note that the data1 name used at the bottom of these two commands has to match what you call the thing when you use the read.table command at the top of the slide. So if you're actually plotting variables in R, the basic command is plot, but you have to variously specify all these different things. So the axes title, so whether you want lines or dots, dots is often simple, so is the default option, and it's sort of start with the default option and then use something more complicated if you need it. Now scaling, now this works is that you need a set of commands xlim and ylim to specify the limits rather for the x-axis and the y-axis respectively. And how this works is this is a sort of vector or ordered list. So you have the C there to sort of make sure that you bring these things together. Lower boundary matches this upper boundary in the brackets, and again C here concatenation, so this joins together this lower boundary and the upper boundary in the brackets. It's usually best to stick with the default options and then use something more complicated if you need it. And then the plot command, similar to eViews, you apply the thing to the X variable first and then the Y variable. So our simple lecture example, so plot price against the gold price, call the X label price and the Y label. It'll still work if you don't do that, but it'll act these slightly strange names. So here is the graph that's produced then. So this suggests that the two variables are indeed negatively correlated. Okay, this is the graph that we saw before in the beginning of the lecture, so we've got the same basic ideas as these sort of three cartoon graphs that we've seen in lecture 1 and lecture 3, but we've now got a plot that's not perfect, okay, but you shouldn't have to sort of change your glasses to sort of see that there is a hint of a negative correlation between these two variables. You would still need to cross-check the results of this graph with a formal statistical regression analysis, okay, and what I would say here is that again, I didn't always have the experience and the maturity to realise that, although it sounds sort of trivial mathematically, it's well worth actually plotting these variables just to sort of check that what you think is going on is actually going on. Okay, and what I wanted to sort of say here is that even as this subject ramps up in difficulty and we apply more advanced regression methodologies, the same basic idea applies, as we've seen both in these cartoon graphs in the first few lectures and the basic ideas that you've been introduced to with straight line graphs in high school maths. Okay, so there's lots here that's liable to look harder than it really is, and you shouldn't be intimidated by it. It's possible, about R squared here, this is probably more important in years where there is an exam compared to when there isn't. Uh, the usual way of teaching this is to sort of say that as part of this module, you need to demonstrate an ability to understand and interpret output, and R squared is one of the quickest and easiest things to make sense of. So if you run a regression, both eViews and R generate R squared values automatically, and the basic idea is that the R squared statistic gives you the proportion of the variation in the data explained by the regression model. So essentially, the higher the better, because you want to explain as much as possible in the data. Now there is an important caveat. So R squared automatically increases as additional x variables are added to a regression model. Now this happens even if those x variables don't actually lead to any improvement in the regression model. So there is a sort of potential pitfall here. Now, as a sort of countermeasure to that, an adjusted R squared statistic can be constructed that takes into account the fact that the R squared automatically increases as you add additional x variables, but for whatever reason this R squared statistic, even if it is a slightly clever idea, isn't widely used. So some observations about R squared then. So R squared lies between 0 and 1, and the basic idea is that if R squared is 0, the model explains nothing. If R squared is 1, the model explains everything. Generally, the higher the value of R squared, the better the model. And textbook examples often have high R squared values like 0.7 or higher. Now, if you're writing teaching material and textbooks as I have, it's quite nice if you have high R squared values. Unfortunately, real life isn't always as perfect as that, okay? And it's possible that lower R squared values might actually still be useful, even if not great. So there's no hard and fast rule about the interpretation of R squared, and in contrast to some of these textbook examples, usually an R squared value of say 0.3 or higher is enough to say there is a non-trivial amount of variation in the data explained by the model, and it may not be publishable, but it's of sufficiently high value to be useful, even if 0.3 doesn't sound a particularly high value. In our lecture example, for instance, there's an R squared value of nearly 40%. So there's a demonstration of here that's a relationship between the stock price and the gold price, although it's clear that other factors also affect what is ultimately going on. And that's why this value of 40% higher. So I wanted to try and show you where the R squared statistic comes from, and that's what I'm going to go through partly on this slide, also in the next slide. And what we've got here is an analysis of variance table for a regression model. Now this is something that's important for historical reasons. It's important in terms of some of the R commands that are used. Okay, but I think really the importance of this for this course is primarily just it explains some of the terminology used in R, and it's important historically in terms of the evolution of the subject and the contribution to applied statistics of people like John Tukey. Now, it says here the table shows that the R squared value is equal to this thing here minus the sum squared error over the total sum of squares, and I would probably suggest you ignore most of what's on this slide. Just if you construct it like this, that tells you that the highest value that the R squared can possibly be is equal to 1, and the lowest value of the R squared can be is equal to 0. Okay, and then it's just that this subject of analysis of variance was important historically.